Hi everyone. In this video, we are going to continue to discuss our example using what we are now going to state and show, which is a Kummer's theorem. So that's a theorem that we'll prove in the next part of the course, but I just want to show you, how powerful it is and how it is used to get a sense of what are the rational points and general prime divisors in an extension field. Okay, so recall that we are looking at our usual curve, but now over F5, just to be for concreteness. I mean, the field arithmetic does actually change the prime divisors that you have, but for concreteness, let's consider F5. And if you remember, I mentioned this a theorem that says that if you have a what we'll later call tame cyclic extension of the rational function fields, namely extensions that are obtained by adding an n foot for any n that you would like of some rational function, like an element in K of x, under some conditions. In particular, the characteristic should not kind of disturb things, and also you need the GCD of these n i's and n to be 1 and so forth. But this is quite general, and it in particular captures our example of y squared equal x cubed minus x, regardless of the arithmetics. And the theorem that accompanied to that kind of extensions, like extensions of the rational function fields, well, you add a radical like that, an n square root, an n foot, tells you that you can actually, first of all, compute the genus, maybe last of all, but you can compute the genus quite easily. You can just read it from the defining equation, which is kind of nice. Also, the full constant field is K. Right, you always have this issue that when you extend K of x, you may add, like in the example that we once did, constants. So maybe you start with a 5, but in your field extensions, you maybe unintentionally added an element in F25. And this is not a desired property. You want to stay with the same field of constants, or at least you want to know what is the field of constants, because the function field is defined with respect to that. And so the theorem tells you that K is indeed the full constant field, which is very nice. And it tells you exactly what are the prime divisor lying above the irreducible polynomials in the defining equation, and they are totally ramified. It talks about the divisors above infinity. Here the situation depends on the GCD of n and this kind of degree of the right-hand side of the polynomial defining equation, the rational function defining equation. And 4 seems to be like a small item, but actually it's quite an important. It tells you that no other prime divisor other than those appearing above, other than those P1, PS, and potentially P infinity, ramify. And that's going to be important for us. We will need to know what are the ramified places. And item 4 tells you that you don't have to look any further. Only P1 up to PS and this P infinity. In a subsequent video, you'll see an example where the fact that we don't know where the ramified places are makes things more complicated. Okay. But anyhow, using this, we essentially got to the point where we know that the GCD is 1. So that's this thing. Sorry, the genus is 1. And we know what are the places above P0, P1, P minus 1. These are the roots of x cubed minus x and P infinity. And actually all of them ramify. So so the theorem that we showed told you that all of these ramify, like totally ramify, namely E is n, like as large as it can be. So when I say totally ramify, I mean that. When I say ramify, I just mean that E is larger than 1. But in extensions of degree 2, once it's larger than 1, it's the maximum possible, which is 2. And over P infinity also, you have only one prime divisor, and it totally ramifies. And we also said that we can, if you remember, it is useful to and informative to specify a prime divisor using a local parameter or a uniformizer, sometimes it's called. And that's just a function that has valuation 1 at that particular prime divisor. Right? We know that there is always a function with valuation 1 because we defined VP, if you remember, it was quite a long time ago, VP was chosen out of the congruent class of evaluations to be that one that has an that is on to Z. So there's always something that is that sends in some function that sends to 1. And another way of saying that is that such an element satisfies that MP is T times OP, right? So any function that vanishes at the prime divisor, at the point, is a multiple of T. A multiple by something in OP, something that's defined. So 1 over T is not fair. You can't put 1 over T here. Okay. So that was that. And we showed that the we showed that the local parameters, so obviously the local parameters downstairs in K of X, we know them. So, right, so this is an example of a local parameter of P0. It is a function that has a unique 0, like 1, 0 at the point 0. You can also, of course, take something like x times x, that's x times x plus 1, say, that's also fine, or even x over x plus 1. I mean, there are many choices for picking MP. Actually, for picking a local parameter, actually, once you pick a local parameter, you can multiply it by any unit from OP, and only units from OP. So for example, x plus 1 is a unit because it has no 0 and no poles at 0. And 1 over x plus 1 is also a unit because it doesn't vanish and it doesn't have a pole at 0. When you plug 0 to 1 over x plus 1, you get just 1. So really, a local parameter is determined only up to a multiplication by a unit from this ring, exactly, right? Because a unit from this ring is exactly, in terms of valuation, it's exactly something that has valuation 0. So if S, say, is a unit of the valuation ring, then the valuation of TS, where T is some local parameter, is the valuation of T plus the valuation of S. And now this is 0 and this is 1. So this is indeed 1. So really, if you multiply by any unit, you'll get another local parameter. And if you think about it for a second, that's the only thing that you can do. Because, this has to be 0 in order for 1 plus this to be 1. So, and the elements that are sent to 0 by the valuation are precisely the units in the valuation. And yeah, that was a bit of a detour here, but what I'm saying is that local parameters are useful in order to describe and work with, actually, also, not just describe, also work with prime divisors, which, currently are kind of abstract objects. So they're kind of getting less abstract when you do that. Of course, another option, and we will do both, is to use kind of coordinates. So for example, when you write P0 here, I think of the point 0, like in the line F5. And 1 is also in F5, and infinity is like in the projective line F5 in a sense. So there is also this point at infinity. And also for these, we can find, and we'll do that later on, we can describe them not by local parameters, by like a pair of elements. So this would be, for example, P0, 0. And this is 0 because, y is 0 at 0. And this is P1, 0. So I'm taking this one from here. And the 0 is because of the fact that y vanishes at 0. And this is also P minus 1, 0. And this is, there is no great name for it, but you can call it just P infinity infinity or something. I don't know, just P infinity, or maybe Q infinity or something. Because once there is only one prime divisor above infinity, usually you call that prime divisor at the upper layer also a place at infinity, or prime divisor at infinity, or just the point at infinity. Sometimes there could be like several places above infinity, and therefore you don't have one place at infinity, and it kind of loses its meaning. It's like places above the place at infinity. Anyhow, so that was last time. And the next thing we want to do is to analyze the other prime divisor. So like in F5, you have also P2 and P minus 2. So you want to figure out, if you put P2 here, what happens above it? Is it like this? Is it like that? Is it equal to F equal 1? Whatever. Okay, so this was the computation of the local parameters. Okay, and in order to do that, we are going to use a heavy tool called Kummer's theorem. And this slide is kind of a mouthful, and it actually does contain a lot of things, but let's go through it slowly. So from here on, unless I'm saying otherwise, and I don't think I would say otherwise, we are only considering finite separable extensions of function field. So f over L is a function field, E over K is a function field. And when I say that f over L is a finite extension of E over K, recall it's the same as saying, I mean, by definition, is saying that f over E is finite extension, but that's equivalent to saying that L over K is a finite extension, and also that for every prime divisor, P from below, like P in E over K, and capital P in F over L. So if you look at the corresponding residual fields, so yeah, usually you call it like that, then the index of that field in this superfield is also finite. Right, all of these three conditions are equivalent. So anyhow, that's when I say finite. When I say separable, I mean that f over E is a separable extension. Okay? And we will later see what it tells you about the other things, so L over K and so forth. But just, you know, when I say separable, I mean f over E is a finite extension. And it is a theorem that if you have a finite separable extension, then it's called the primitive element theorem. We'll talk about it. Then you can always generate the bigger field using just one element from the smaller field. That's called the primitive element theorem because that's kind of the primitive element. But anyhow, just assume, even if you don't know that we are in a situation where f can be generated by one element, let's call it y, from E. Okay. And now let's consider a prime divisor P. So this is a prime divisor that lies below, so in E over K. And you should think of, you know, what we're trying to do is to figure out what are the prime divisors above P. And we are going to use Y to do it. Okay, so the order of things you should consider is that you're given f over L, a function field extension, you know, separable and finite, of E over K. And now you take a prime divisor at the lower level, and you are going to find a Y, even though here Y is written before, you're going to find a Y such that this holds, it generates the entire field of functions and some other condition. So what is other condition? What's written here? So what I'm requiring is that this Y is in this new ring that we haven't seen so far, but we're going to see it quite a lot, this O prime P. And O prime P, actually, there are two ways of defining it, equivalent ways, of course. One, which is approachable to us right now, is as the intersection of all valuation rings corresponding to primes above P. Right, so you have little p here, this is E over K, and then, you know, maybe you have P1 up to PR, infinitely many places above P. Now with each of them, right, so this is OP, with each of them you have a valuation ring associated to it. And what I'm saying here is that I'm looking at this intersection, the intersection of these valuation rings. Note that it contains OP, by the way, right? Because I mean, the easiest way to see it is like in terms of valuation rings, because OP is obtained by OP1 intersection E and also by OP2 intersection E and so forth. Also in terms of valuations, you know that all the valuations here are positive or non-negative, and also here, because you just multiply by the ramification in it. Anyhow, but it could be the case that each of them is larger than OP. I mean, each of them will be larger than OP because the functions here are from F, not just from E. But moreover, it could be the case that their intersection even is not exactly OP. I mean, no reason for that to happen. I mean, there are functions here that are in F and not in E, and potentially there is a function F common to all of them, which is not in E. So we defined OP prime to be this intersection. Right, all functions in F that are defined everywhere above P. Now, another characterization of this is is the following. We are looking at all functions in F, all Z in F, that are integral over OP. Right, so here there is no reference to, like explicit reference at least to these valuation rings. I'm just looking at a Z in F, and I'm saying that belongs to the set if it's integral over OP. And recall, integral means that there is a irreducible, there is a polynomial, say the minimal polynomial of Z, a monic polynomial though, that vanishes at Z, and all of its coefficients are in OP. Okay, so for example, like, we did that when we talked about, I don't even remember in what context, but it was some time ago. Okay, we'll see that in a second. So that's another kind of definition or characterization. And the fact that this is equality is a theorem, okay? It will prove. Okay, so again, we start with a prime divisor below, prime divisor of U over K that we want to study, how it splits or how it behaves in F over L. And we are searching for Y that, first of all, it is contained in this new ring that we are talking about. And secondly, together with E, generates the entire function field F. Okay, another result states that in that case, where Y is in OP prime, the minimal polynomial over Y of Y over E, I mean, usually the minimal polynomial is just something with coefficients in E, but in fact, it is with coefficient in OP. That's kind of, not unrelated to this equality. Okay. Okay, so in what follows, what we're going to do is the following. So given a phi that has a coefficient in OP, we are going to define phi bar. So that's going to be a new polynomial, and it's going to be over the residue field, EP, of OP. Right, so it's kind of phi bar is going to be obtained, that's what's written here, by projecting the coefficients of phi modulo MP. So taking a coefficient which is in OP and evaluate it at MP or the point to get a coefficient in EP. So what do I mean by that? So phi bar of T. So by definition, you go over coefficient by coefficient here, and you just take the corresponding projection. And that's one way of denoting that. Another way, which we used when we talked about the coding theoretic, the coding application, is CI evaluated at P, because this reminds us that we think of these as functions and P as a point. And another way of writing that, which we'll use it here, is a CI bar, just as a projection, because P will be clear by context. So we just put a bar here. Okay, so why am I doing all of that? So with these notations and this theorem that I haven't proved and so forth, we have the following. So let's say that F over L is a finite separable extension of U over K, as we just considered. And as before, let's say that we have a Y in F that together with E generates F. And you consider a place, but actually I think of the place coming before Y. Prime divisor at the bottom, that Y, such that Y is contained in this OP prime, the intersection of all valuation rings, capital P is above little p. And now let's denote by phi p, phi of t, the minimal polynomial of Y over E. And as we said, it's actually the coefficients are in OP, and project it down to EP. So let's consider phi bar of t as a polynomial over EP. Now, P itself is, of course, irreducible because it's the minimal polynomial of Y over E. But phi bar may not be irreducible. It could split because you're considering a different polynomial now, related but different. So let's say that when you factor it, it looks like that. So you have R components, these gamma i's to the epsilon i's, where the gamma i's are irreducible and distinct. And the epsilon I just tell you how many of gamma I do you have. So epsilon I is one or more. Okay, so again, you factor Y. You factor the irreducible or minimal polynomial of Y after you project that minimal polynomial to EP, and you look at the components in the factorization. And the Kummer's theorem, this is one version of it. There are more general versions, but I just want to, to analyze our example, so I'm using the simplest one that I can state. So Kummer's theorem tells you that if you happen to be lucky and all the epsilon i's are 1, namely you have factorization to linear factors, you have factorization with no repeated irreducible polynomials, they may not be linear. I mean, gamma I could have higher degree. Then there are exactly R prime divisors. Let's call them, as usual, capital P1, capital PR above P. And we know everything about it. So we know that there is no ramification. So ramification is 1 for each of those. And the f of Pi over P is exactly the degree of this irreducible polynomial. Okay. And the third thing will just allow us to figure out what are the local parameters. So the fourth point is tells you that gamma I evaluated at y is actually kind of vanishes at capital Pi. It's in the maximal ideal corresponding to Pi. But as a forced read, what you should look at these two. What I'm telling you is that there is a way of figuring out what is E and what is F and what are the prime divisor above it. How many are there and so forth above little p, just by doing some factorization over a finite field. That's good. And one more very good thing about this theorem is that it doesn't work only when E is the rational function field, right? So for any function field over K, if you look at an extension of it, the theorem holds. And this is unlike, for example, when we started this unit. So we had this theorem that tells you, so this was the theorem, but it considered this setting. And this setting was, you adjoin y to the rational function field. So it doesn't kind of scale up if you continue like that. So we really do like theorems that don't assume that the bottom layer is just the rational function field, because we are going to construct what's called towers of function fields. We are going to add more and more function fields in the middle, and we want a theorem that holds for all levels. So that's a great theorem in that respect. Okay, so with this theorem, let's analyze what happens to a P2 and P minus 2. So let's see. So we know that y squared is x cubed minus x. And this is the defining equation of the function field. And we know that x cubed minus x is in OP2. Namely, this function can be evaluated at x equals 2. I mean, it is just even a unit there, right? Because when you plug in 2, you just get 8 minus 2, which is 6, which is 1, which is not 0. Okay, so, but certainly there is no issue with evaluating this function 2. And so what this tells you is that y is in this new ring O prime P2, right? Because you can consider this polynomial, t squared minus x cubed minus x. So you see it's a monic polynomial. The coefficients, and the only other coefficient is this one, the coefficients are in OP2. So this means that y is an integral element over OP2, which puts it in O prime P2. So it's kind of easy to verify. I mean, comparably easy to verify that an element is integral is in OP prime using this other characterization. This one, other than the intersection, because you don't know the intersection. I mean, currently we're kind of trying to figure out what are the p's above little p. And this is something that you can do intrinsically over OP, as we just did. Okay, so we know that y is in O prime P2. And since our extension is finite and separable, trust me, we can apply a Kummer's theorem. You can show that using some Galois, but we can apply Kummer's theorem, the theorem that we just stated. And that theorem tells us that we should factor the minimal polynomial. That's definitely the minimal polynomial. It's degree 2 polynomial, and we don't have a degree 1 polynomial that y vanishes at y, because then y would have been in E. So that's the minimal polynomial. And by Kummer's theorem, we need to take this polynomial, project it's modulo MP2, which just means plug 2 into X, really. Right? So, and factor the polynomial that we get. So in this case, we see we have this t squared, and then this expression is just 1. It's 2 squared minus 2, which is 6, which is 1 in F5. And luckily for us, this polynomial now factors as the product of two factors with no repetitions. So epsilon 1 is 1, as epsilon 2 is 1. It also happens to have linear factors, but that's just because it's a degree 2 polynomial, really. And Kummer's theorem tells us that because of that, there are two prime divisors lying above P2. We are going to denote them for now by capital P2 minus 1, corresponding to this, because kind of when you plug minus 1, this goes to 0. And for that particular prime divisor, the third item, this one, told us that the factor that you got is in the maximal ideal. So y plus 1, when you plug y here, y plus 1 is in the maximal ideal that we just found, corresponding to the prime divisor we just found. And the other prime divisor correspond to this, and y minus 1, by the same reason, is in the maximal ideal corresponding to that. And again, we call it capital P2 1, because when you plug 1 here, you get 0. It's just a name. Good. So, but we really want to kind of better understand these prime divisors, and for that, we want to find local parameters for each of them. So, the third item told us that y plus 1 is in this maximal ideal, and a local parameter for us is something that's in the maximal ideal, but the valuation is 1, not higher. So let's just figure out, ask ourselves whether y plus 1 is also a local parameter. This is not guaranteed by the theorem. The theorem doesn't tell you that the valuation of this thing is 1. It just tells you that the valuation of this thing is positive. But let's do the calculation. I think it's a good exercise. So, for just to save some notations, let's denote by this new place that we are trying to understand by capital P, without this 2 and minus 1. And so let's see. So y plus 1, we really want to understand y plus 1, and we kind of understand y squared minus 1, or y squared, because y squared is x cubed minus x, and x we do understand. I mean, what happens in the rational function field in x we do understand. So I'm kind of deliberately trying to relate the thing I care about with the thing I know, which is y squared. So one way of doing that is to notice that y plus 1 times y minus 1 is y squared minus 1. And so, because this is the valuation of the thing I care about plus the valuation of this y minus 1, then I just need to understand this and that in order to understand this. Now, first of all, because y plus 1 is in the maximal ideal, that was the third item, we know that y minus 1 cannot possibly be in that maximal ideal. And the reason is that if both of them were in the maximal ideal, then also the difference between them, which is just 2, and you can't have a unit, a constant in the maximal ideal, it will make it be the entire thing. So because we know y plus 1 is in the maximal ideal, y minus 1 cannot be in the maximal ideal. So this really tells you that the valuation at capital P of y minus 1 is not positive, right? Because it's not in the maximal ideal. But what I claim is that it has to be 0, right? Because I mean, it can't be the case that VP of y minus 1 is negative, right? Why? Because VP of y is at least the minimum between VP of y minus 1 and VP of 1. Right, the usual trick of writing this as this plus that. Now, VP of 1, of course, is 0. 1 has no zeros and no roots nowhere. And VP of y, I mean, y is in OP prime, right? So VP of y, we know that this thing is non-negative because it's the intersection of all O P's above little p. And okay, so and if this were to be negative, so if this thing is negative, then this is a negative, this is 0, they are different. So the triangle inequality becomes strict, and you get something which is negative. I don't know, -3 or something, whatever. And that's impossible, right? Because you can't have this both non-negative and negative at the same time. Yeah, I wrote it here, but I think it was a bit maybe, I think this explanation is better. You need to somehow explain it better. So that's why I'm saying that y minus 1 actually has valuation 0. So let me erase that for us. So this thing is 0. Okay, so the valuation that we care about, I really want to prove it's 1. I want to prove it's a local parameter, is this thing. So now it's enough to consider the valuation of y squared minus 1. And so that's what's written here. And to do that, I'm going to go back to x. So y squared minus 1 is, well, y squared is x cubed minus x. So this is the minus 1. And this thing I'm going to factor as, or if you factor it in over a 5, it's x minus 2. You can kind of easily see that when you plug 2, you get 0, because we said that when you plug 2 here, you get 1. And the other factor turns out to be degree 2, irreducible polynomial x squared plus 2x plus 3. You can check it's irreducible if you want. Or just, trust me. So to recap, we know that the valuation that we care about is this thing. And the expression here inside in terms of x is x minus 2 times x squared plus 2x plus 3. So therefore, the valuation of y squared minus 1 of capital P is the ramification index of capital P over P2, which we know is 1, because Kummer's theorem told us that everything has a ramification in this case. So that's just 1. Times the valuation of this expression. But at P2, at small P2. And the valuation of this expression at small P2 is just 1. Because, in the rational function field, the valuation of P2 is defined to be like how many factors of x minus 2 divides the polynomial or the rational function that you look at. Worrying about signs, plus or minus. And here x minus 2 is one such factor, and this is irreducible, so it has nothing to do with that. So there is only one factor of x minus 2 that divides your function, making this thing equals to 1. Making this thing equal to 1. So 1 times 1 is 1. And so the valuation of y squared minus 1, which is the valuation of y plus 1 that we care about, is 1. And so we see that y plus 1 is indeed a local parameter of this point. And a similar calculation will show you that y minus 1 is also a local parameter. Let me just not do it. And maybe as a recap, so far what we did is this thing. So we kind of understood all of these using the initial theorem that we had, and this using Kummer's theorem. Namely, there are two prime divisors lying above P2. We call them P21 and P2 minus 1. And the corresponding local parameters are y minus 1 and y plus 1. And I don't write anything here in terms of E or F, because you can see from the picture, if you have two prime divisors lying above you, then E and F has to be, each of them has to be 1. Also here, I don't write F equals anything 1 because E is 2, F has to be 1. Because the sum of the EI's Fi should be 2. Okay, so as I said, so far we did that. Let's just finish by doing the same calculations, but more briefly. Figure out that over P minus 2, you have these two prime divisors. So again, we're looking at P minus 2. And again, because y squared equals x cubed minus x, and x cubed minus x is also like well-defined at minus 2, and then you plug in minus 2 here, you don't get like infinities. I mean, you can plug in anything but for infinity, you won't get infinities, just a rational function field. So what we have is, by the same reasoning, that y is also an integral over OP minus 2, right? Because this is its minimal polynomial and it's monic, and the coefficients are in OP minus 2. So by Kummer's theorem, in order to figure out what are the prime divisors lying above OP minus 2, what you need to do is you need to take this polynomial and project it now to MP minus 2, which again means just plugging minus 2 to x. So when you do that, you get t squared plus 1, which actually in F5 is does factor to t plus 2 and t minus 2. So again, Kummer's theorem tells you, because the epsilons, the Kummer's theorem, as I stated it, we are going to see more general versions, applies because the epsilons here, the multiplicity of each of these irreducible polynomials and factorization is 1. And so the theorem tells you that there are two prime divisors lying above p minus 2. We are going to denote them as before by p minus 2 because of this, and minus 2 because this vanishes at minus 2. And p minus 2 plus 2 because of that. And you can show again that y plus 2 and y minus 2, which the theorem tells you are in the corresponding maximal ideals, actually are local parameters by the same calculation. So that's why in this picture, you have p minus 2 here with its local parameter, and you have these two prime divisors above it with these corresponding local parameters. And since these are the only rational places of f5 of x, right? We know that at f5 of x, you have a rational place for every element in the field and infinity. The other prime divisors, there are infinitely prime divisors here, but they are not going to be rational. They are going to correspond to irreducible polynomials of larger degrees. And the degree of the prime divisor is just the degree of that irreducible polynomial. So this is all you have. So this means that these are the only prime divisors. I mean, each of them are the only rational prime divisors in capital F, right? Because all of them are rational, because these are rational, and F is 1, right? F here everywhere is 1. I didn't even write it. And the degree of this thing is F times the degree of that thing, right? The degree of a prime divisor is F of capital P over small p times the degree of little p. Because L is K. Right, if you remember, maybe I should remind you of that. We had K and L and O little p and O big P. And this thing is the degree of capital P. I mean, the degree of the extension. O capital P contains a copy of L, and the extension degree of these fields is degree capital P, and the degree here, for same reason, small p. And this line here is f of p capital P over small p, and this is just L over K. So generally speaking, the degree of capital B times L over K is the degree of small p times the residual index. But in our case, since L is K, the constant field remains the same, you get that the degree of the larger prime divisor is the residual degree times the degree of the smaller prime divisor. Okay, so these are the only places that are rational places or rational prime divisors of capital F, because by this equation, if you will not be able to find a rational place of F lying a non-rational place of E, right? If you take some prime divisor here, which is not rational, and you'll take a prime divisor above it, then because of that, I mean, you can't have that this is larger than 1 and this is 1. Right, a rational place of capital F is a degree 1 divisor, but if it lies over a non-rational place, then already that degree contributes more than 1, and this could be 1 or more, but anyhow, it doesn't matter because that cannot hold. Okay, so we found all rational places. This is essentially all solutions to the equation y squared equals x cubed minus x over f5. Namely, you only allow x and y to be an element in f5 or infinity, like the projected version of f5. Okay. So what are we going to do with this? So just for fun, we are going to construct, we are going to play with Riemann-Roch spaces and construct a little code out of this. It's not a very not a very useful code, but it's a code. It's going to be optimized. So let's see. So in order to construct the code and talk about Riemann-Roch spaces, let's first recall that the principal divisor of x as an element in the rational function field below is p0 minus p infinity, right? Because x has a 0 at 0, a simple 0 at 0, and a simple pole at infinity. And so x as an element of f has a prime divisor, a principal divisor, which is, well, you need to, take those, look at the prime divisors above each of them, and multiply the ramification index. Right, so if you look at our picture, x as an element in F5 has a 0 here, and a pole here. So as an element in capital F, which is this thing, it has a 0 here, but with e equals 2. So you need to have this e, and a pole here. Again, equals 2. Right, this is just because, if v like p0, so this is because v capital P00 of x is e of P00 over p times v small p 0 of x, and that's 2. Right, so the fact that x has a simple 0 at p0, so this is 1, implies that this is 2. And so when you write the prime divisor or the principal divisor of an element, you write the valuation at the point. So this is exactly this times the prime divisor. And same here. So here you have minus p infinity, and this minus becomes 2 here, because also the ramification index of p infinity over small p infinity is 2. And also importantly, there are no other prime divisors appearing here, only those. Because prime divisors that are not written here, it means that the valuation of x at those points is 0, which means that the valuation of x of prime divisor above those points is also 0, because they're just 0 times the ramification index, which is 0. Okay. So in any case, this is the prime divisor, the principal divisor of x in the larger function field. And now I want to figure out what's the principal divisor of y in the larger function field. And so to do that, first of all, I know that if something appears in the principal divisor of y, so if the valuation of some prime divisor, which I want to figure out whether it appears in the principal divisor of y, if that happens, so namely the valuation at capital P of y is not 0, then that's the same thing as saying that the valuation of y squared is not 0, right? Because this is just twice that. And the reason I'm doing that is because y squared is related to x, because y squared is just x cubed minus x. So these two things are equivalent. But the point here is that now I only have x's, so I can go downstairs and say that this is equivalent to v of little p, where little p is the prime divisor lying below capital P of x squared minus x not 0. So what I'm saying here is that any capital P that participates in the principal divisor of y must be above small p for which this holds. Namely, I look at this function and ask myself what are the prime divisors for which this either has a 0 or pole. Right? Larger than this larger than 0 means a 0, and this smaller than 0 has a pole. And we know that. So we know that x cubed minus x has zeros at p0, p1, p minus 1, and also p infinity. There it has a pole. And so the only possible prime divisors that can appear in the principal divisor of y are the places lying above these places. And if you remember the picture, we had just one above each. So it looks like that. So it's this, and so these are the only prime divisor that can appear as a in the principal divisor of y. Right, so that's what's written here. And right, and actually, previous calculation that we did show that the principal divisor is actually precisely this thing. So, for example, P00, but each of them is kind of for the same reason, appears with a coefficient of 1 because the valuation of y at those points is 1. This is something that we did before. I can scroll it and find it somehow. But maybe we did in the previous example, I'm not sure. Oh, yeah. We just happened to find it by accident. Good. So the valuation of those alphas for each of these alphas is 1. That was nice. Good. And this we also did. We actually showed that when we computed it equals 2, we showed that the evaluation of y at infinity is minus 3. Okay, you can try to just redo it yourself using the fundamental equality. Just playing with y squared equal x cubed minus x and see what happens. Good. So in particular, I care about the pole divisors of x and y. I mean, so far we said that this is the principal divisor of x and this is the principal divisor of y in F. But I'm looking at the pole divisors. So you see the pole divisor of xf is 2p infinity, and the pole divisor of y in F is 3 times p infinity. So that's what I wrote here. And this means that I can start kind of finding functions in Riemann-Roch spaces corresponding to r times p infinity for r going between 0 and so forth. So for example, because these functions don't have pole anywhere else. So for example, L0 p infinity, well, that's just the 0 divisor here. And so we know that L of 0 is just k, or F5 in our case, which is just the span of the function 1. So 1 is a basis for this Riemann-Roch space. Now, 1 is also an element in L1 p infinity, just because this contains that. But as you'll see in a second, there is no other function. The dimension of this is also going to be as the dimension of that. It's going to be 1 and not 2. Potentially, it could have been 2. But there is no function here. You will see in a second why. But in L2 times p infinity, you have not only 1 as a field as a basis, but also x, right? Because x has 2 poles at infinity, so it satisfies the requirement to enter this Riemann-Roch space, namely, x plus 2p infinity is at least 0, because it has 2 poles at infinity and it has no poles anywhere else. That's important. And if you allow for more, so you increase the divisor to 3 times p infinity, then you also get y. Right? And of course, it's clear that x and y are independent, and x and 1 are independent, and x and y are independent, and so forth. Because if they were linearly independent, it would still be in f5 of x, the rational function. And right, in 4, you can actually get also on top of this 3, you could get x squared, right? Because when you square x, you multiply this by 2. And in f5, you can also add adjoin xy, because like valuation at infinity, the new infinity of xy is the valuation at infinity of x plus the valuation at infinity of y. and this is 2, and this is 3, so it's 5 altogether, and so forth. In 6 you can get x cubed, and you can see that actually from essentially this point on, every time you increase this number, you can find another function, another way of combining x and y's. It has something to do with the fact that these are co-prime, but I mean, the fact that they're co-prime means that you can find combinations of them which give you 1 and so forth, but I don't want to use negative coefficients, because then I don't want to see y over x, because y over x doesn't sit in those Riemann-Roch spaces, because y over x has poles because of the zeros of x, which are not cancelled by the zeros of y. But anyhow, we just kind of populated these Riemann-Roch spaces using these functions. And what I claim is that you have equalities throughout. So it's not like I missed a function. These are the functions that appear now. And to see this, recall that this picture that we had when we talked about Riemann-Roch or corollaries of Riemann-Roch. So we said that if you consider degree versus dimension, so you look at degree 0, 1, 2, and so forth divisors, not necessarily r times p infinity or anything, whatever you want, and you consider the corresponding dimension. Then we said that once you reach 2g minus 1, from this point on, once the degree reaches 2g minus 1, the degree minus the dimension is fixed to be g minus 1, no matter what divisor you take. So you get maximum deficiency, but you get that deficiency, you know that you get it. I mean, it's good and bad. It's bad that it's a deficiency, but it's good that you know what's going on. So from the 2g minus 1 degree, the dimension has to be g, because the difference is g minus 1, and so forth. And we know, for example, for degree 0, the dimension is 1, because that's just k. And technically, you don't know what happens generally between them, between 1 and 2g minus 2. We did say that at degree 1 and degree 2g minus 2, we know what happens. We know that the degree could be g or g minus 1, for example, in this degree, depending on whether or not the divisor is canonical. And also here, depending on it's 0 or 1, depending on whether or not the divisor is principal. But in our case, anyhow, g is 1. We calculated the genus. It turned out to be 1. And so in our case, actually, it's kind of funny because 2g minus 1, just 1. So it's just here. It's like 2 times 1 minus 1. So we know that from this point onwards, right, that's this point. From this point onwards, the degree minus dimension has to be g minus 1, which is 0, because g is 1. So actually, we know that from this point on, these two numbers should agree. So we didn't miss any function, right? So this is exactly what we had. So, right, so the dimension of this is 1, because like this one, dimension of this is 2, because we have x and y, and so x and 1, and so forth. So actually, what we found are bases for the corresponding Riemann-Roch space. So actually, with this, we can construct some nice code. So we can construct a length 7, again, a very small code, a length 7 GOPA code over F5. And the way we're going to do so, so we are going to use P infinity as the one determining the Riemann-Roch space. Essentially, like when you do Reed-Solomon, so you take polynomials of degree at most R. Here, it's not quite degree. I mean, actually, in this case, it is, but with x and y's. So here we're talking about degrees. So here, the Riemann-Roch space corresponding to P infinity, we said it's actually spanned by like simple monomials. You don't have like 1 over x appearing there or anything more complicated. So actually, these are polynomials, but they are not quite polynomial. I mean, they're polynomials with the relation y squared equals x cubed minus x. And the degree of the polynomial is actually the degree of x in a sense is 2, and the degree of y is 3. Because degrees are now actually valuations, not degrees per se. You don't have a degree 1 polynomial. Well, because if you take a polynomial in x and y, the degree will be at least one of those, like a triangle inequality. So But anyhow, you can think of this as kind of polynomials in x and y, but the degrees should be like should be weighted with 2 and 3 correspondingly. And the evaluation points are going to be the points on the curve. So you see you have these 7 points, because altogether we find 8 points. So you have 0, 0, 1, 0, minus 1, 0, and so forth. And so these are, if you go back, these are these points. So you take all of those except for the infinity one. You can take the infinity one if you want. You need at least one prime divisor to be left out. It doesn't have to be rational, but to be left out so that you can use it to define the Riemann-Roch space from which you get your function. So we took it as infinity, like in the classical case, but you could have. And I know it's not, these are not many points, these are 7 points. But the nice thing that this is over F5. So, you know, it's more points than you're allowed to have in your field. So even though it's a small example, it already bypasses like a little bit the restrictions you get when you do read solver. Okay, anyhow, so this is the code. And we are going to choose R to be free. And if you remember, the Riemann-Roch space corresponding to 3 times P infinity is spanned by 1 x and y. So this means that a basis for the code is obtained if I'm going to replace these z's by 1 x and y. So, you know, this thing, x evaluated at P0, 0, and so forth. This is one vector in the basis of our code. This is another vector. And the all ones is also another vector. Because when you use 1 here as a basis, when you evaluate 1 everywhere, you get just once. And if you do the calculation, you see that this vector corresponds to this vector. Right, this is because x of P0, 0 is 0. I mean, we made sure that the force coordinate is exactly what you get when you evaluate x at that point. So x of P0, 0 is 0, and x of P1, 0 is 1, and x of P minus 1, 0 is minus 1, which is 4. If you put minus 1, the identification is weird, so I wrote 4. And similarly, this is why you have a 2 here, and a 2 here, and a 3 here, and a 3 here. And as for the y, so this vector, this basis element just translates to this one. So you see, this is the second coordinate now, 0, 0, 0, 1, minus 1, which is 4, 2, minus 2, which is 3. And this is the all ones vector. So this is a basis for our code. And the code is obtained by taking all the linear combinations of it over 5. So, you know, clearly it has dimension 3, because this has dimension 3. And the distance, recall, or at least the bound on the distance is n minus k minus g plus 1. You know, in our case, this plus 1 is not negligible. So n is 7, number of points that we took. K is 3, that's the dimension of the code. G is 1, that's the genus of the code. And the plus 1 appearing here, altogether gives you a 4. So you get a distance for code length, block length 7. And just recall that, I mean, technically potentially you might have wanted to get like an MDS code, namely a code in which d is n minus k plus 1, like matching the singleton bound that we proved. So potentially you could have gotten distance 5, but this has no distance 5. And according to a sketchy internet search I did, a bit lazy one, I don't think there is such a code. So I think that the best thing you can do for length 7 codes over 5, at least for linear codes, give you distance 4. Okay. So anyhow, it's not an important code, it's just so that the dots, just to connect the dots for you. Now, let's finish this example. Actually, we're going to delve deeper in that example in the next unit, but let's finish that particular video with talking about the canonical divisor of our function field. So, you know, the canonical divisor is a difficult object. It's, you know, it's the divisor corresponding to a differential, and differentials are kind of abstract. They are based on models which are abstract by themselves. But we have this characterization that tells us that a divisor is canonical exactly when the dimension of that divisor is the genus, and the degree is twice the genus minus 2. So for genus 1, and particular for our case, but generally for genus 1 function fields, the dimension should be 1, right? G is 1, and the degree should be 0, 2 times 1 minus 2. If you think about it for a second, you know such a divisor. The 0 divisor satisfies that. It has degree 0, it's the 0 divisor. And it has dimension 1 because the Riemann workspace there is exactly K, F5 in our case. So kind of weirdly enough, the 0 divisor is a canonical divisor for our or for any genus 1 function field. And that's actually very interesting because it's kind of, this is an if and only if, right? So if that happens, then the genus has to be 1. So that's a characterization of genus 1 function fields. And if you remember, the canonical divisor, actually class of this is a class of divisors, right? When you mod out by the principal divisors. So what we're saying here is that actually the class of canonical divisors for genus 1 function field is precisely the class of principal divisors, right? Because any principal divisor has a degree 0 and dimension 1, because they also participate together with 0 in the same class. So there is a weird coincidence here that tells you that the canonical class, the class of canonical divisor is the same as the class of principal divisors. And the class of principal divisors correspond to function, and the class of canonical divisors correspond to differentials. And so this means that there is some duality in genus 1 function fields between functions and differentials. And I can't say much more about it because we didn't talk about differentials, like non-veil differentials, the usual way of talking about differentials. But that reflects kind of symmetries that you also explore in the recitations when you will talk about the group law of elliptic curves, genus 1 function fields. But that will be later.